Well, let's start a new recording. Okay. So pulse spreading is the spreading of a ray over distance, right? That makes sense. And what happens is when we're using light and you have critical rays and actual rays, then the actual rays are going to get to the receiver before the critical rays. So you're okay on actual rays and critical rays. That makes sense? So the actual rays are the ones moving down the center. They're parallel to the cladding, or the core, I guess you'd say. And then critical rays are the ones that's doing what? They're parallel to the critical angle. And then all your other rays fall in between these two. So the actual rays are going to get to it first. The critical rays are going to get there last. Because if you get above the critical ray, you're going to have refraction anyway, right? You understand? So we're going to have rays moving down the light that's going through all these different angles if we don't control those angles. Now, single mode controls the angles. So in single mode, all we have is actual rays. In multi-mode, we have critical rays, we have actual rays, and all the rays in between. Does that make sense? So the rays in between the actual rays and the critical rays don't have a name, but they're all in there. All light travels past between the actual rays and the critical rays, exit the end of the fiber at different times, will always be between the two. That makes sense? Everybody okay? Any questions? So what this is going to happen is in the fiber, this is going to create what we call pulse spreading. Your actual rays are going to hit the receiver last. Your actual rays are going to hit the receiver first. Your critical rays are going to hit the receiver last. And the pulses on being received are wider than the pulses being transmitted. And that's what we're doing with this. That's the way we modulate it. We just pulse the light. So the light's pulsing real fast when it moves down there. And of course, that would be the bits per second that we're trying to send, or hertz we're trying to send. So here's the actual ray, here's critical rays, and all the other rays are here, somewhere in between. So this is just an example of what would happen. So the original signal, I think the arrival time of all rays, right? And then, of course, what's going to happen, the original signal is the received signal is actually going to be what? It's going to be lower because of attenuation, but it's going to be spread out because of spreading. Are we okay? So we could end up with garbage like this being received. Or we could end up with garbage like this, which really causes a problem in the cable. Because now what we're getting received is not exactly what's being transmitted, right? Everybody okay? We could actually receive the wrong information. If we use the wrong cable, if we use the wrong light frequency, and this all depends on the length of the cable. So the further the length of the cable, the more spreading you have with the pulse. Or if we control the light or the path. So this is a modular dispersion. This is what we call dispersion. This is what happens when we have critical rays and actual rays. Mode. So y'all understand now. So we're going to have multi-mode or single mode. What is a mode? Drive through the core, yeah. So multi-mode means we have multiple paths. Single mode means we only have what? One path. Single mode cable or single mode fiber only has actual rays. Multi-mode means we have what? We have more than one path. So multi-mode is going to have more model dispersion than single mode. Material dispersion, light traveling at different regions of the core, will move at different speeds. We already know that. Chromatic dispersion means that if I use light of different color, And this gives you problems. Light of different color, when they hit those, when they reflect, they're going to reflect at different angles, right? You understand? Just like a watch, just like a prism. So your high-speed lights will use one. So this is why single mode cable usually uses what we call a laser. You know what laser means? It's an acronym. Anybody heard that before? Yeah, and it's got an S. Most people put a Z in there, but it don't. So laser. It's light amplification by stimulated emission of radiation. But basically, this is one color. So if we use a laser, then that means we do away with chromatic dispersion. The problem is that lasers are a lot more expensive than regular light emitting diodes. So we use lasers for extremely long distances, right? You understand? If we're not doing extremely long distances, then we're going to use light emitting diodes. So we use light. Light travels to different regions of the core, will move at different speeds. So if we can make it travel in the same region, then we got really, really good signals and really, really good speeds, right? Are we okay so far? A lot of stuff. Multimode fiber, this is what we're dealing with. Fiber that allows light to travel different paths through the conductor. Typical core sizes are 50 micron, 62.5, which is widely used, and 100 nanometers. It usually uses an LED as a light source. We have two types. We have called stepped index, which is the cheapest, and then we have graded index, which is a step up from that. Okay, so ours is graded index, 62.5, 125 fibers is what we're going to be playing with. This plastic right here is stepped index. You will not find plastic in graded index because they just can't make it. So this is stepped index fiber. And then graded index is glass. Of course, we could have stepped index glass too, but no. So stepped index is this garbage right here. So what we're doing is we're shooting light down through there. We're not controlling the path. The light follows. The light's bouncing off all over the place. We have actual rays, we have critical rays, and we have everything in between. This is stepped index. This is going to be the cheapest fiber you can get. So plastic is stepped index. Now what they do on graded index is they do this. They come in and they literally have all types of, so it's made, this is made out of the cladding. Then 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9 layers of glass that has different coefficients of refraction, different index of refraction. So what happens is that when it moves through here, it bends a little bit when it goes through each layer. And then it hits the cladding, and then it'll start moving through. And then it'll do like that, which is really, really neat. We call this graded index. So what happens is in a graded index cable, the light moves like this. So notice it's more controlled. So some of them are taking these. These will take the longest to get there. This is your actual rays. But we're controlling that bounce. And this is graded index. This is going to be your second fastest cable out there. It's a graded index. This is probably the most popular. Costs more. Graded index costs a pretty good deal because you can see putting all those glasses in there together is going to be complicated. Getting them all the same size, keeping your ovality, your centrifugal, how centrical, you know what I'm trying to say. The core offset, but this is what we got. So we got graded index, multi-mode. As soon as I say graded index, you know it's multi-mode, right? graded index, 62.5, 125 fiber, with a 250 micron coating and a 3 millimeter jacket. Outside jacket, excuse me. So this is graded index. This runs really, really well. We don't have all these different rays. They move at pretty much well the same speed or close to the same speed. Stepped index, you got light arriving at the other end all over the place, right? You understand? But it's going to be the cheapest. If you get plastic, this is what it's going to be. The most popular multi-mode cable is, so y'all know what multi-mode means. What is mode? Well, the mode is a path the light takes down through the core. If we say single mode, it's got how many paths? One. If we say multi-mode, we know it's got more than one, right? If we say stepped index, that means that sucker's just stepping down the sides, right? Graded index means we're going to do what? We're going to curve it. We're going to deliberately curve it through the core. So the core is actually got different glasses in there. Yeah, we have two types of multi-mode. Yeah, we have two types of multi-mode. We have stepped index and graded index. We have one type of single mode. And how can you make it travel one path? Well, you make the core so small. So you make the core extremely small. So these are the 9, 10 nanometer cores on the single mode fiber. So this is what they're talking. This is the index of refraction. So this is the core. This is the core. This is the clad, and that's what causes it to bounce back. Graded index is like this. So we actually change the index of refraction over the core, right? You understand? Which causes the light to do what? We got one that travels down the center, which is your actual rays, but your other rays that's moving between the critical rays are actually being slowly bent as they move through the thing, which is pretty neat. So this would be what they call the graded index profile for graded index. Graded single mode allows light to travel one path. It requires an extremely small core, and we use laser lights for these things. So believe it or not, multi-mode cable is more expensive than single mode cable. But what makes the multi-mode cable or graded index is more expensive than single mode cable. Where you get the cost benefit from multi-mode graded index is the end electronics. So we use LEDs and phototransistors. Very simple end electronics. Single mode requires lasers. So if you ever look up a laser LED, the price of a laser LED and a laser LED and then just an LED, you'll see, laser LEDs in this mode cost maybe $200-300 a piece. An LED that runs at 850 microns might be 15 cents. So graded index, if you look at the price, graded index multi-mode cable costs more for the cable, but it's so much cheaper for the end electronics. So there's where the cost advantage comes from. So single mode, we just use extremely small cores. And the light can't do anything, right? You understand? I mean, just got one path. Stepped index multi-mode, cheapest cable, cheapest electronics, slowest speed. Graded index, most expensive cable, cheap electronics, faster speed than stepped index. Single mode, cheaper than graded index cable, most expensive electronic connectors, but we have the fastest speed. So your connectors are more expensive because they got to be aligned a lot better, right? You understand that? So the connectors are more expensive for single mode. The end electronics is a lot more expensive. So of the three, it would be, we use single mode for what? And long distances. We use single mode for long distances. Well, we can get pretty good speed on multi-mode cable as far as networking goes. You know, in networking, we're still at around 1 gigabit per 1 gigabit per second. Multi-mode can handle that, no problem. Which system is more expensive? Not cable, which system? Which one? This is the most expensive system. This is the next most expensive. This is in the middle, and stepped index is the cheapest system. Now, when we're talking about system, we're talking about not only we're talking about the end electronics, right? You understand, and the fiber itself, and the connectors that we need to splice them and terminate them. So if I was going to do a short run, like in industry, odds are we're going to use what? Stepped index, right? If I'm going to go a medium-sized run at extremely high speeds, I'm going to use multi-mode. If I'm going to go long-distance runs at high speed, we'll use single mode. So Bell South probably uses single mode cable. We have fiber running from here to the Birmingham campus. That's single mode fiber, right? Running from a building down here is multi-mode. And you can tell multi-mode has an orange jacket on it. See the orange jacket up there? Is that orange? Yeah. That's like multi-mode has an orange jacket. And then single mode uses a yellow jacket. And then they have different colors. There's a standard color code, but those are the two primary colors that I've ran into. And that's the outside jacket, not the buffer, not the inside buffer. It's the outside buffer, which comes into the cable. And these are comparisons, just looking at them. So you were looking at this guy right here, 62.5, 125. This would be a 10 125, which would be single mode, which odds are with that fiber scope, we couldn't see the core. So that's a times 100 fiber scope. We do have some time 200s, but when we use the times 200s, the dang core gets too big and we can't see the rest of the termination when we do it. So what we do is, did y'all see the scuff marks on there? When I pass those around, that's where it's actually sanded down. So we'll show you how to put those connectors on there and how to cut them. We don't, in fiber, we don't call it cutting, we call it cleaving, by the way. How to cleave it to get a perpendicular thing, and then how to sand it down and all kind of neat stuff. It's a little harder to do, but it's once you do it, if you imagine you do it over and over and over again, pretty much, well, you'd get very proficient at it. Terminating or putting connectors on there are pretty complicated. So there's companies like AT&T that sells what we call pigtails, which is a piece of fiber that's got the connector already on there. They put the connector on there for you, and then what you do is you splice it onto your cable, usually with a fusion splicer, which we'll look at that too. We have two types of splicing mechanisms. We have what we call a fusion splicer, and then we have what we call a mechanical splice, and you'll get an opportunity to do both of those. And then we have show you all how to use the test equipment where we can measure the dB loss the dB loss of the system. We can measure the dB loss of our cables and all kind of stuff. It's kind of like the little well, it's not the same, but y'all remember the cable the Ethernet cable checker we showed y'all? Well, but this actually gives you the actual dB loss of your connectors and everything, which is pretty neat. Some of y'all are through, so some of y'all are ready to start your fiber. So we need to get far enough in the lecture so we can start working on the labs. And I think the first lab that we're going to do, let me look at our first fiber lab and see what it is, because I know these long lectures get boring, but we don't want to go to the lab if we don't understand what we're doing in the lab, right? So labs. So our first lab is how to strip fiber optic cable. And we're going to strip, and when you strip the fiber, these lengths basically have to be pretty much well perfect, because these things are going to have to fit into a connector. They're going to have to fit into a splice. We don't want a mechanical support with the conductor itself. Your mechanical support is going to be between the buffer and also the Kevlar and the outside buffer. So that means when we do these connectors and we do these splices, if you don't strip these suckers right, copper, we're okay. I always say, well, we don't want any insulation under the screw, and we don't want any wire exposed past the edge. That's pretty easy. So you got a little leeway there on copper that you can deal with, right? When we crimp, we say, okay, we want the jacket to be inside the outside, but it's exactly how far it goes in there. As long as it don't get in and you're crimping on the connector on the insulator, it's okay. But when we start getting into fiber, these lengths are got to be almost perfect. So if you cut them too long, that means you're going to expose some of the glass to us and it's going to break. If you cut them too short, they're not going to go up and butt up against what they're supposed to butt up against. So normally what we have is we have a template that we can lay the fiber on. So normally when you buy a connector, it'll come with a template like this, and you can literally do what? You can lay it on there and make sure it matches there. Some of them gives you links that you have to strip this stuff to. And we got several strips we're going to have to make for ours. We have the outside jacket that's going to have to be stripped to a certain length. We have the Kevlar that's going to have to be cut to a certain length. By the way, you cannot cut Kevlar with regular scissors. So you buy special scissors. They're called Kevlar scissors, and these suckers are not cheap. So don't ever catch anybody cutting anything with these scissors. These are Kevlar scissors. These are sharp enough to cut what? Kevlar. But if you dull them, then you're going to have problems. So we're going to have to cut the Kevlar to a certain length. And we're going to have to cut, if it's a what we call a tight buffer. And what does tight buffer mean? That's another term I've told y'all what it means. Tight buffer. So we're using tight buffer cable. What did I tell y'all that means? Did that just fly by y'all? Tight buffer means that this buffer right here is in contact with the coating. It's contacting the coating. Loose buffer means that buffer that's between the coating and the outside, it's not touching. So loose buffers we use in underground. So what they'll do on a loose buffer is they'll fill it with a gel to keep moisture out. We use loose buffered in something that's going to be vibrating all the time. So the fiber conductor is actually riding inside a tube, and it's got a lot of flex. So the tube can do what? Can vibrate, and the core has no problem. So we have two types of buffers. These right here, these inside buffers. They can be what we call tight buffered, which means it's in contact with the coating, right? Some say with the cladding, and which is wrong, because when they say with the cladding, they forget about the what? The coating. So we have three things. We have a core, we have a cladding, then we have a coating, right? A buffer coating, and then we have a buffer. That would be the actual conductor itself. That buffer can either be an inside, it can be a loose buffer or a tight buffer. So we're going to deal with tight buffer cable, or conductors. Then this would be the conductor itself. So that makes up the conductor. Then we got some more protection for that conductor because it's made out of glass, guys. So what do we got? We got this Kevlar, right? You understand. And then we're going to have an outside buffer. And when we pull this stuff, what are we going to pull it by? What would you think? If we pull this stuff, we have to pull fiber. I mean, we have to pull cables to conduit, right? Or fiber, we usually don't call it conduit. They call it ductwork or ducts. Okay. What are we going to put? Which one of these things are we going to pull it by? What do you think? Just right off the bat. Pull it by the Kevlar. That makes sense, right? So we'll cut all this stuff off. We'll pull out the Kevlar by itself. We'll strip it. We'll have a pretty good size of Kevlar. We take the Kevlar and pull it around the fish tape or around the pulling rope, tighten it down real good, twist it, tie it in a knot, tape it up real good, pencil it down so it'll pull okay, and we pull by the Kevlar. If we pull by the glass, as soon as we pull on it once, what would happen? It'd break. So good job. So we're going to learn how to 6-inch cable. Let's see, debris bag. By the way, this is made out of glass. We got Kevlar, which is not like fiberglass, but it's real thin. We've got glass, though. In glass, we've looked at this with a fiber scope, so it's very small. And if you get that stuff stuck in your fingers, it's going to cause you problems, right? So what we're going to do is we have what we call stripping pads, which are black, so it makes the fiber show up real easy that we'll put down. Then you're going to, when you cut that fiber, as soon as you cut the glass, you're going to do what with it? You're going to put it in a little scrap bag. It's nothing but a sandwich bag is what we got. We use those because it's pretty cheap. More expensive would be a little container that has a twist thing on it that opens and closes, and you just throw the whole thing away when you get through. Here, we just throw the sandwich bags away. So we'll use sandwich bags to keep up with it, or it ends up with all over the place. So that's what it says. It says you're going to get a debris bag. When we clean fiber, we use rubbing alcohol. We don't use rubbing alcohol. We use what they call syringe grade alcohol. Regular rubbing alcohol is about 70% alcohol, so it has a pretty good deal of impurities with it. Syringe grade alcohol is at 91% alcohol, and this is what we'll use. You can buy alcohol pads for fiber. They cost a pretty good deal of money, but it takes a little time. Also, we have to use lint-free wipes because when we clean this stuff, we don't want to leave any residue on it, because if we stick it inside a connector and it's got fibers on there, then it's going to cause problems, right? Especially if they get in front of the connector. So this is what we're going to do. We're going to cut a 9-inch length of cable. We're going to use what we call a 3-hole stripper. And what's nice about the 3-hole stripper is that it's got all the 3 strippers you need for 165 cladding. This is for your outside buffer. And this is for your inside buffer, your tight buffer. And this right here is for your coating. And then once you do that, you might have to do the coating several times. You need to be really careful with stripping the coating, because now you're on that glass. So if you've got shaky hands, you're not going to be able to work with fiber. When we was in the Navy, we had a guy he was from Texas. Of course, we called him Tex. When he got nervous, his hands would shake. And it was so funny watching him solder. He'd be doing this, and he could solder better than anybody you could see. He got himself in sync, but old Tex would start shaking. He got out there in one of the planes, and he was taking off a big old relay, and he didn't put a sign up there on the plane telling nobody to turn power on. And old Tex got in there inside the what we call the load cell, not the load cell, the relay room, which nobody could see you, and he was taking off a relay and had a screwdriver down in there, and somebody come on and turned on power on the airplane, and had all this power. We had 240 volts AC, 3-phase, and Tex blew that screwdriver up trying to get that thing out, but true story. So let me pause this and show you how we're going to do this. Let me bring up the camera. Of course, it's called zip cord, so we can just take it and do what? Split it over. Normally, when we send this, we send it two conductors, one will be transmit, one will be received. And then when you cut the Kevlar according to the length, we come up here and we do we take it, twist it together. Now why am I doing that? To get all the strands together and a loop. And then we'll cut this to the proper length with our Kevlar scissors. See that? As soon as I do that, I'm going to take this and put it in my scrap bag, right? Because this stuff gets all over the place. Then I'm going to have my 3-hole strippers. So the big one for your tight buffer. I'll lay it out. I'll mark off where I want it to strip at, right? You understand that? So we got some black fine tip magic markers or markers in there that you can mark them on the template. We'll mark off all we want to do. We'll come up here. By the way, let me go back to the start. So I'm going to push this back in there. First of all, this is what you'll get right here. And the first thing you're going to do is you're going to mark your outside jacket. Right. You're going to take the outside of the 3-hole strippers right here. You're just going to close it. You're not going to twist or do anything else. You're just going to close it. Then you're going to grab this and twist it and pull it off. Make sense? Then what you're going to do is you're going to mark where you're going to get your template or your ruler, and you're going to mark where the Kevlar needs to go. You're going to take the Kevlar, you're going to pull it down to the side, and you're going to do what? You're going to twist it. And once you get it twisted, mark where you want to cut it. Then you'll get your Kevlar scissors and you'll cut it at that length. And then you'll put this in the scrap bag. I didn't get me a scrap bag. Then you're going to take your conductor. You're going to mark where you want your tight buffer cut at. Then you're going to go down to the next one right here. And then you're going to strip off your tight buffer. Now what you need to do, this is glass. So if you got to strip off a lot, what we recommend is you do it in about 1/4 inch increments. So instead of trying to strip it all the way down from here, you come up here and strip off right there. Right? Understand and do what? You have about 1/4 inch till you get it the length you want. Because guys, it's glass, and we've exposed this glass to us now, right? And, it won't focus in, but you can see the coating on there, the buffer coating. The buffer coating careful we set it in that little groove, because if you don't, this will cut it. It might take a couple of stops to get all the coating off of the buffer coating off there. Okay. We're not going to touch the fiber now. What we're going to do now is we're going to get some. That sucker's really exposed, so be careful. I mean, right now, if I hit it, it would do what? It would break, yeah. The alcohol you can buy from any pharmacy. Sorry, you won't be able to buy it at Walmart, but this is 91% isopropyl, so they call this syringe grade alcohol. Any pharmacy sells it. Of course, we come over here and put some alcohol in there. Then what do? Put the fiber in the center like this. I don't break it. And then we close our fingers around it like this, and then we just pull it out, wipe it a couple of times, and then that should get every bit of the coating off. Now this guy is ready to terminate. It's either ready to terminate or ready to splice. But for these connectors, these links are critical because they got to fit in the connector exactly right. You understand? It's got to fit in that connector exactly right. So the splice is going to either crimp down on this guy or it's going to on this. Now, mostly on splices, we crimp down on this one, but then we put it in a protector we call a splice tray. Your connectors are going to cramp on to this outside jacket and the Kevlar. And if you don't have it cut right and you get it down in that connector and then you try to get it out because you cut it too long or cut it too short, then odds are you're going to try to, the glass is going to break, right? And this is glass, guys. I mean, good gracious. I don't have I mean, all we got to do is it's gone. So it's glass. It might be very, very flexible, but it's glass. And if you get that stuff in your fingers, and don't ever do this, right? And by the way, you get into laser. A lot of these laser wavelengths are lasers you can't see. Laser is amplified light moving at one frequency. So, they cauterize eyes and stuff like that with lasers. They do laser surgery where they literally cut off they reshape your cornea so you don't need glasses anymore. So by George, if you come up here and you're trying to see the light and you look down in the end of that sucker, you could be damaging your eyes, right? Y'all understand that? So you can look at fiber in a fiber scope when it's inactive. If you don't know what the other end of the electronics is, and you're trying to look at it with a fiber scope, don't do it, because the other guy could be generating light pulses that you can't even watch. You can't see, and it could be damaging your eyes. So be careful. Be careful with it. So that's basically what this lab is about, is just learning how to cut it to the right lengths. Let's see if we're going to use a cleave. I need to show you a cleave. Let's see. No. We'll look at actually trying to get a perpendicular cut on our fiber later on. Strip jackets, cut to length member, remove buffer, clear coating and to a specific length. And then what we'll do next one is I'll show you how we can actually cut the fiber. We don't ever cut the glass fiber. I'm sorry. We can cut it with anything. But the problem is if you cut it with a regular pair of cutters, you don't get that perpendicular surface. It'll be fractured. It'll be at an angle and stuff like that. So we have a device called a cleave or a cleaver that we'll show you how to use, where you actually come and take it and cleave it at a perpendicular angle. And then we do that for splicing. And then when we put it in a connector, we actually sand it a little bit to make sure it's perpendicular. We'll show you how to do that. But that's probably it, guys, on the fiber. A lot more complicated, but there's the people that can do this, it's a lot harder to work with than copper. But if you just follow some procedures, you'll do a good job. Are we okay? So that's the first fiber optic lab that some of y'all are ready to do. And like I said, I'll cut y'all the fiber links that y'all need. I think it said this one might be long enough. I might be able to cut that. I don't know if we got enough room on our cart to bring out the fiber tools and keep the copper tools on there at the same time. Some of y'all are still working on copper. Y'all that's fixing to go on the fiber, I'll show you where the stuff's at. And right now, y'all can just go into the storage room and get it. And then when everybody gets through with their copper lab, we'll swap the supplies over on our cart. And that way we can roll them in and out without you having to go back into the storage room. Any questions? Okay, so some of y'all need to do what? Some of y'all need to go ahead and finish up your copper today, and then and then try to move into fiber. And all we're going to do the first lab is just learning how to strip this stuff. Then the next class will show y'all how to do the dB meters so you can measure the loss of a cable. All right, guys, let's go to lab. What does it say? 6-inch length. All right. I can get a few out of there. Oh, where's my cutter? Where's my cutter? I'll have to buy some more rulers. I'm getting broke up. Is everybody here? No. There's something else I needed to show y'all. Oops. Get me a bag. Who's out here? Which one? That one? Okay. Uh-huh. This is guys, so I'll just have to show James when I give it to him. What did I do with my scissors? Okay, guys, y'all. What we're gonna do in this lab, I just thought about these when I was cutting these short lengths. It's going to be impossible for you to strip that without the conductor moving out. Okay. So what we're going to do on this, we'll never, ever, 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 ever do this again. Is we're going to come up here and we're going to tie a knot in the end away from the one that you're doing. Y'all understand why? Because what happens, the length is so short. When I come up here and start stripping this stuff, uh, what's going to happen? Huh? It's going to, yeah, the conductor will move out. And so, and you'll constantly be doing what? Pushing it back in. But now, since we got it tied in a knot, see, it's not going to go anywhere. So now you can strip it and all kind of stuff, which would simulate having a long cable. So when y'all do this lab, first thing you're going to do is the end that you're not working with, you're going to do what? You're going to tie it with a knot, and then that way you can cut it, you can strip it, and this conductor won't come out on you. But we never actually do this on a real cable, because what probably just happened? I probably broke the glass. Now I didn't inside the jacket, but I probably broke it inside the tight buffer. But it's no big deal. The tight buffer is what's actually holding it in there. I can't break break the tight buffer, but yeah. But now we can play around with it. So that's what I want to show. So we're dealing with a real short length, and right now if you tried to strip it, it's just going to pull out, and your strip length will keep changing. Right? So okay, that's what I want to show you. Here, put those back in there for me, Chase, if you don't mind. I think it tells you in the lab to tie it, but I've got people doing connectors and they'll tie them in a knot like that. And I said, no, you don't do it anymore.